thank you. If you want to open, here's the link. You can just put it on your laptop. If you want to open the link, you can just put it here on your laptop. So.
Can you make that a little bigger?
Yeah. Is it good? Welcome everyone to this workshop and to this track. So, as Navid said, we're here to present our work on the NLP system, and which is to be deployed on the Deep platform. So we will explore various challenges we encountered in our work, going from the data to the models to the results, and we'll try to make this session. We'll try to ask some questions, have some discussions, some ideas in our work. So here, first of all, if you have any feedback about anything, or if you want to contact us, there are some links either on the Slack or on the Skype, or by contacting us by email. Then, as Jimena said, just a general overview of the DEEP. It's a collaborative platform for qualitative data analysis, supports humanitarian people to produce analysis. It improved a lot the humanitarian data ecosystem, and it's now one of the largest repositories in data. Now, the assisted tagging tool is just aims to the mic, okay.
Want to check up that everybody has a link? Could you get it open? So that would be basically, if you go up, maybe see the link again. So that would be a link to a Google Cloud, which you can just run it on your account.
The very top.
Can you scroll up?
Yeah, sorry.
Yeah, sure.
You just need to write this.
You just need to write this link here.
So bit.ly 36P8LMH. Yeah. So
Write it on a thing and just pass it also on paper.
so just raise your hand like if you don't have it, or is it okay for everyone? Otherwise the guys are gonna go check. It works for everyone? Yeah? No?
Okay, so can you hear me? Is it good right now? Okay. So in this notebook, we're going to have a simplified version of our NLP system. We have our code, but we're just going to use a chunk of our data and a lower number of epochs just to show our implementations, etc. So the main objective of our tool is to improve and speed up the analysis of the humanitarian text. So we provide, as you just saw, live recommendation to humanitarian taggers. So right now, our data comes from our data is annotated, comes from specialist taggers from the Deep. And just like Navid said, the authors of, so we're the DeepL team in data-friendly space, myself, Nicolò, Ranjan, who couldn't join, then Benjamin and Oguz, and we're supervised by Iwan, Patrice on data, Navid on technical things, on modeling, and Jimena, who's our Deep product manager. So first of all, you'll see that you'll need to just clone a repo, then install the requirements. We'll try to go through, especially the data, the things we did itself, not just line by line coding. So for what we're going to talk about is the data, the specifications and the challenges, the models, the implemented methods and their impacts, and finally the results. So first of all, let's have a general overview of the data. So the data is extracted from humanitarian documents. So we have a total of 86 labels. into 8 different categories, which we call the primary tags and the secondary tags. The primary tags, just saw them in the deep, they're the sectors. The 1D matrix, which we call the 1D subpillars, and the 2D matrix, which is with the sectors. Then there is the secondary tags, the affected groups, demographic groups, which are more specifically the age and the gender, the specific needs group, the severity, and the geolocation. So in this notebook, we're going to focus a bit more on the primary tags, just to have an understanding of everything. So for the primary tags, we're focusing on the sectors, which consist of 11 labels, 2D subpillars with 18 labels, and 1D subpillars, 33 labels. We're just now showing a little overview of the data. Here are the sectors. For example, you can see agriculture, education, food security, etc. Then there are the 1D pillars and subpillars, which are just like which are in a hierarchical way. So there are the pillars, for example, here casualties and context, etc. Then the subpillars, which are more specific things. Okay, so the main difference between the 1D pillars and subpillars is that the sectors and the subpillars 2D are linked together, whereas the pillars 1D are just independent from them. So here we have just an example. Here is the entry. Then we get the sectors, which are linked to the 2D pillars and subpillars. And finally, we have the 1D pillars. As you say, we can have, it's not single label, it's multi-label, it's a multi-label setup. And we have a total, we work with a total of approximately 160,000 entries collected from the deep. So first of all, we just see the tax distribution. Here is the X. The X is just each bar just contains one tag. Then it's the occurrence probability in entries, and you can see that it's very underrepresented. Some examples about that: 19 tags are present in less than 1% of the data, and 34 in less than 2%. But in the other side, we don't have many tags that are overrepresented. Only 6 tags are present in more than 15% of the data. After that, we have the languages. So French, Spanish, and English. English takes the biggest part. Then French and Spanish are approximately the same. And yeah, these are the main things about the data. It's just like we said, multilingual, many tags to be handled, and imbalanced repartition. Do you have any questions about the data or anything? No questions. Okay. Yeah.
Wait.
Data labels again,
Okay.
a bit slower so that the audience.
Okay.
Yeah.
So for the labels, we have what we're focusing on are the sectors, the subpillars 1D, the subpillars 2D. The sectors are just no hierarchy, just agriculture, education, cross, etc. Then we have the other labels which are hierarchical. We have the pillars and we have the subpillars. And the pillars and subpillars 1D in our data, they are divided into categories: the 1D pillars and the 1D subpillars. The 2D subpillars are linked to the sectors. However, the 1D pillars are independent from them. This is the main thing.
Is that clear for everyone? Yeah? Good.
Thanks. So now our first point of discussion, and now we would like to have your opinion, is what do you think the best data augmentation techniques that would work, or what would work the best basically for our problem?
So from here on, we are going to draw a little from your expertise. What will you do with this data given this unbalancedness?
Yeah.
So, I mean, this is just a personal thing that I've been working on recently, but we've been trying to do data augmentation techniques where we just randomly delete some data and then we can generate more data from this. So that's
Randomly
something we've been trying recently.
random
with-
deletion.
Yeah.
Yeah, thanks.
If you can also introduce yourself for your name or your organization.
Oh, yeah, sure. Hi, my name's Haley, and I work at the German Research Center for Artificial Intelligence, and I'm a PhD student.
Okay, random deletion.
Hi.
Hello.
So I wanted to suggest that probably we have to do tokenization, right? So we have somehow to tokenize our data, and we also have to normalize the data. Yes?
Okay, we did not really go into that because just like we're going to say, we just used some pre-trained models. So just about the data augmentation.
Okay.
Thank you. Navid.
Hi, so I'm Yassine. I'm a UPFL student in data science. So maybe you could also use translation on, for example, on English or in which language you want to add some data and to use like what you can extract from that.
How do you do that?
Like, for example, try to translate some of the English data into English, some of to Spanish, sorry, some of the Spanish to English and this kind of things.
Okay, thanks. That's actually that's exactly what we did. So, as we also did the random deletion. We tried some basic data augmentation techniques: random deletion, random swapping, synonym replacement, changing the numbers in an entry just to generate more entries. But it did not really perform. Did not give you really good results. So what we went on and what we kept is data augmentation with translation, and exactly built on the fact that we're having 3 languages. So if the language is Spanish, you translate to English and French, and if it's English, you translate to French and Spanish, and so on. So yeah, exactly. So here we just begin to show our implementation, just the importing the data. So here we have in our sample we have 10,000 samples in this notebook, and we keep the 50 most present tags for simplification and to have the results. Then now we want to define our train, validation, and test set, because since the data is very imbalanced, so we want to have a fixed test set. We don't want it to be random, because we want to have clear results and clear understanding of each model. So we do a stratified train test set. So we create a unified testing set, and we want to keep the proportion of tags the same across all, especially the test set and the training set. We can do the training on it. So here in this notebook, for example, we do the stratified stratified splitting for train, validation, and test set. And here we check that the number of labels is the same for all.
Yeah.
So
Selim, sorry, is it possible for us also to run the code?
yeah, totally. I'm just not running right now, not to lose
Yeah.
time.
So can you also run that just for everybody to test? Maybe just is it also possible for everyone to run the code? Just give it a try. Yeah.
Yeah, I think they could.
Okay.
So here, yes. So now we just talked about the data. Are there any specific other questions about the data before we can move to models, or? Yes.
Subsampling the majority classes?
Sorry?
Did you try to subsample the majority classes? So when you have a big data imbalance,
Yes.
so sometimes you take from the class that is more represented a less number of samples. Did you also try that?
We tried it, but we also
understand, yeah.
one of the main objectives of the project was also to have the best results possible on the overrepresented data, because statistically it's the one that comes the most for humanitarians. So it doesn't. The overall purpose is not to just balance it, but we just wanted to make the best out of all the data possible, and undertaking undersampling some tags we tried it, and it just lowered the performance of the best represented tags, and we don't really want that either. I don't know if
Yeah, we try oversampling of the underrepresented and undersampling of the main categories, but yeah, there are some very common techniques, SMOT algorithm, and combine under and oversampling techniques together. But in general, in NLP, I like this one because you have to make this thing with a point, with an embedding, okay? You don't generate a new sentence, okay? So in most of the cases, it doesn't work because you create a fake point in your system, in your labels distribution, but it's not the same like have a new sentence that it's different from the others. Okay.
It's really an ongoing challenge for our system that actually these classes that don't have much of data for that are working not very well. So we try very different sampling methods, but this data augmentation, this simple data augmentation, do not really bring anything special for us. At the end, that was after 1 year of different methods that we tried. So if there is, it feels to us that it's kind of like a research area by itself, that more related to fusion learning, et cetera, that how can you really support these underrepresented classes? So ideas for master thesis.
Okay, so that's it. That's all about it for the data. So now we move to the model. We first began by implementing a fast text baseline model. So not very dummy, but yeah, it's a good baseline. So here we work with the one versus all loss, and we just get the predictions. The code takes approximately 5 to 6 minutes to run on Google Colab to get the predictions, and then we have all these we use. So for the metrics, with the precision, the recall, then the F1 score, and the Hamming loss, so here, for example, we're just giving some examples of results. It can go from tags that are really not performing well, so context, demography, displacement, number of people affected, etc. in this baseline, and it goes to some tags performing quite better, COVID-19 especially, and some sectors with food security, education, wash, and health. And you get after that, just to have a general idea of how it's working, we get the arithmetic mean of all tags, which for the F1 score is 0.39.
Do you want? Maybe we can run. I don't know if you see also the outputs in the published Jupyter notebooks. Yeah.
Yeah. If you go to runtime at the top, and then click run all, then you can basically run the entire thing and see the outputs, and also like change some things.
I think you can rerun it on your own. I'm just choosing not to run it. Mm-hmm. Yeah, because it takes some time to yes.
Is an article recognized correctly if all the tags are found, or if one tag is found?
So we have first we have the article, and the user, just like you said, gets the entry. So the user selects 1 sentence, 2 sentence maximum. So the user selects an entry, and that entry is fed to the model, and the models are trained on already selected entries. And this is the main objective. This is why it's assisted for now, and it's not completely independent. It still needs the user to get the text, to get the live prediction and then to validate it.
Yeah, I mean, picking up this question is a little feel us better about the problem. So the way it works, as we see in the demo, so there is first a big document. This could be 5 to 10 pages, and then we are working actually on an automated system that tells us which part of this document are important, but at the end it becomes like a 2 sentences, 1 sentence, just excerpt. And this classification that we are running here is basically given one of these text excerpts does a prediction about the class of that, and these are basically, the sentences are IID, so they are separate than each other, they're independent from each other. Yeah.
Okay, then so last results on the fast text baseline. We have more tags that are performing bad than well. Tags with low performance are 17, then 20, then 13. So the models also, we see that they're performing heterogeneously depending on the tags, and we have more tags with low performance. So do you have any questions about the baseline model before? Okay.
So it's basically a trained fast text, right?
Yes.
It's also trained or fine-tuned, basically.
Exactly. So right now the second point of discussions is, so now we want to create our own model, and what do you think it should satisfy? What do you think the specifications are and what it should satisfy?
So how would you go for it now that you know the data, the baseline to see? What would be your approach for this classification problem? I mean, we spent a year on that. So
Okay, so the model biggest specifications is that it's multilingual. So it needs to work with especially English, Spanish, and French. It needs to have a good performance, otherwise it's useless. The predictions need to be fast because we're doing live predictions. It needs to handle an important number of imbalanced tags. This is very important. And finally, we want to optimize the deployment costs because we want to put as least money as possible for the deployment. So yeah, this are the specifications. So the second point of discussion is about what are the best models to deal with the multi-label data. We're using deep learning and backbone fine-tuning. So what do you think the backbone should be? How it should look like? What are the metrics we should use for training? And finally, do you have other methods that could optimize the results after training?
Maybe to start out in regard to the metrics that you want to use, I'd say the recall of the class you want to label is, you want to predict is really important. Because, for example, if a document were to be labeled as a crisis or something like this, you don't want to miss it. So you rather have a model that is predicting too much of them, but not to lose some of it. So the F1 score will be really helpful there because it's going to give you a compromise between the recall and the precision. Also, and I'm jumping ahead there to talk about the other method to optimize the model afterwards, sorry. We've been working a bit with active learning where I work, and this could be something interesting when you have evolving context, new sort of data that you don't have yet see. And you don't want to lose all your previous training, and you want to keep the labeling effort as low as possible. So you want to specify what new data would be relevant to label, while keeping the previous training relevant, while using still the previous training, and minimizing the labeling effort as much as possible. So yeah, this is all. Yep.
We are not doing any sort of active learning, but how was your experience or approach?
So it's still a work in progress in our case. What we do is that we deploy a strategy that is actually used to retrain the model over time. We do have some sort of model that is used to predict the relevancy of news, financial news. And in this context, we know that the global evolution of the markets and stuff like this is going to have a relevant role on whether or not the news would be relevant or not. And in that scenario, we would need to have a model retrain over and over, but this is a huge task. We are talking about thousands of news that need to be labeled by your professional teams, and we don't want to have them do that over and over. So what we are proposing to do, and what we are still studying at the moment, is to use those active learning query with our trained model from a set of data that has been costly labeled to specify what are the new news in that regard that would be relevant to get the label from. And hopefully it would output the, for example, the text that have not yet been seen. Let's think, for example, about the Ukraine crisis or anything like this, something new that you don't yet that you have not yet seen would come up in those queries and would need to be relabeled by the team. Well, it's a really special use case for us, but would apply to anything else. You could also have a model who will, a scenario where you would refer to news that have been hard to label, where the model was a bit more hesitant to label it as relevant or not, or stuff like this.
Thank you for this. For the active learning, it's we still did not implement it yet, but it's definitely a part of our future work for this project to be able to learn of the new labeled data, and we're also doing some monitoring on the label on the models to see how they're performing and see how they're evolving with data towards, for example, concept drift, etc. So yes, the active learning is definitely something that we want to jump to. So maybe I can share what we did. So first of all, for the backbone, we're using Hugging Face. We're using an extremely distilled backbone. Distilled is task agnostic distillation from BERT models. Consists of 6 layers, 256 hidden size, 12 attention heads, and which gives a total of 13 million parameters. It's chosen especially for the low time and memory complexity, which will help us make predictions as fast as possible and without needing big memories on the GPU while deploying. Then for the metrics, you're right, recall is very important, but there are also other things. We don't want to over-predict. We don't want to do over-predictions because there are taggers, and we don't want to enter in the problem of biasing the taggers, etc. So what we chose is we work with the beta F1 score. It's like the F1 score, but just we can just change the beta. With the beta inferior to 1, we have the precision favorite over recall, but we still want to have the we don't want to lose the general performance, so we choose the beta of 0.5 for training and especially validating the datasets. Then right now we're talking for the primary tags, which are the sectors, subpillars 1D, subpillars 2D. We're having 2 trained models. First one for sectors, because the two have different structures, the labels. The sectors are just trained in an MLP architecture way, so then you have the backbone, then you just have the output layer. We have 10 or 11 separate heads depending on the number of tags, protection, agriculture, or each head for a different tag. And then we have another model for subpillars, which is trained differently in a multitask learning way. So here, for example, we can see the architecture of it. So we have six layers in our backbone. The first ones are the same for all, but then the last hidden layer is different for each different task, and we define a task for the pillar. For example, the COVID-19 pillar is a task, then the impact pillar is a task, etc., etc. And at total, we have 13 different tasks. So the benefits of this is that it helps us anneal further the problems due to data imbalancedness, and in the same time deal with a big number of different tags in one model, because if we just do an NLP-like architecture for like 50 tags, it just won't work and the models won't be able to learn from it. After that, after training, we also do something, because then we train, then we generate the predictions, we get the logit of it, then there is a threshold where do we choose the model or not. And we worked on that, and so after we train the model, we generate the logit predictions, which we can call the probabilities, on the validation set. And on that validation set, we tune the threshold so we can maximize the metric, which is the F-beta score, which we already talked about. So this enables us to have different thresholds for each different tags, and this helps us first to prevent models from overtagging, and helps to adapt to the data imbalanceness problem and to the fact that models learn differently across different tags and are differently confident about predicting different tags. So, for example, if a model predicts 0.5 for COVID-19 deaths and 0.5 for agriculture, there will be only COVID-19 deaths that will be output, because this one is lower than the threshold. Do you have any questions about what I said?
Yeah, sure.
Just a remark. These thresholds are, or the outputs of the model, a fixed number. There is a paper, I think it's what is called trust or not to trust classifier from 2018. It helps to generate a number so that you can see how much the model trusts its own value, and that could be beneficial. And for instance, only considering giving a label only if the score of this trust score is high, and maybe, for instance, especially if the user has to tag it and there's some kind of automatic filtering for him, that's the relevant text that you can say, okay, this tag, the machine is more or less certain about it, and this tag, he's not so certain about it. That might be helpful, and especially you could also use this instead of applying the threshold to the direct output, applying it to the trust score. This is one technique from these guys from 2018. There's a different technique for also giving uncertainty about this. It is called Deep Ensemble from Google, but of course they would have to train multiple models, and that would be not the best thing if you want to, if you want to restrict or reduce the costs. Yeah.
We went through the second paper. Thanks a lot for your remark, for your input. We went through the second paper, and yes, there is the problem of having many models and then not being able to log them because of the memory and time place. But to be honest, for the first paper, I did not go through it, so we will work on it. Thanks you.
Very, very good idea. I mean, but then probably we need to have some metrics of uncertainty there, which is the usual methods are either ensembling or ensembling through dropouts. So kind of MC dropout that then needs several forward passes, which then, let's say if we want to keep also the response time very low, so we don't have the capacity, or maybe we can have parallel ones, and then at the end you have some sort of standard variation of the different scores can be seen as the uncertainty of the prediction. Yeah, that's good. But yeah, definitely that's also one of the challenges here, let's say that our predictions are not really well calibrated. And this definitely becomes more acute when it goes to classes, underrepresented classes, that we have more uncertainty, definitely. Yeah, that's very, very good point. Thank you very much. Any other question? I mean, just to wrap up till this point, so our system is working as follows, and correct me if I'm wrong. So we have a multi-label, so every document or sentence that we are putting in, we need to predict multi-label from that. It's mostly single label, but in many cases we have multi-label as well. So the way that is working is that we have, like, let's say 3-4 layers of transformers that is common between all the labels, and then there are some transformers that are specific to each class that predict a binary classifier. It says whether this class is in or is not in. So each of them gives us a value between 0 and 1, and then we need a threshold and say that everything lower than 0.3 for that specific class is non-selected, and everything higher than that is selected. And this threshold that we are fine-tuning basically is different for each of the classes, basically. And yeah, an idea would be that you can maybe also use uncertainty to calibrate these scores better. This is just a big picture. Any idea, point?
With respect to this trust or not to trust, I think there's a quite new package, Deep Check called, not from you probably, and there is, and I think they have it implemented already, this kind of score relation. So you don't, because if you look at the paper, it's yeah. It is some kind of things you have to implement for it, some kind of density estimation and so on. So maybe you can directly leverage it and try it out. Yeah.
Thank you very much.
Thank you.
I can also short. Just a question about, I think I haven't fully understood the architecture. Yeah. So you said those shared Hugging Faces layers, and then how does it come, the single models you have then for each sector, you have a single classifier layer, but how is it? Is it like, I don't know, what's the graph behind it? Is it?
Selim, I may try. You correct me if I'm wrong. Maybe you go to the figure that might also explain some parts. I mean, our first model was for every class we had a different transformer, different BERT that predicts something. Not exactly BERT, but that specific 6-layer distilled BERT. But then we thought that maybe this class, and that was a binary classifier for every class. And let's say we have 12 class on sectors, we have 50 class somewhere else, so there are a lot of classes here. And we thought maybe these classes are also helping each other for this classifier, so maybe we can do some multi-class learning. So the way that it works, and that was Selim's idea, that let's say we have just one transformer, that the first 4 layer of that is common between all the classes, and then each of these classes have 2 layers of transformers which it learns some class-specific characteristics, and after that it has one vector. This vector goes to a binary classifier. So it's basically one model with 12 heads, let's say, but these heads are full transformers that are the last pre-trained layers of this BERT model. Yeah, so, yeah. And it really improved the system. These classes really transformed something between each other.
So at the end, how big was the model in megabytes?
Sorry?
The overall model, how big it was? Because you said you had several transformers. No?
In the end of the day, we were talking about it, and I was just going to mention it at the end. In the end of the day, the models do 0.2 seconds per entry for the prediction, and the total memory is 530 approximately megabytes. We have 3 models overall. Now we're just showing 2, and the third one we just deployed. And yes, overall we have 530 megabytes of memory used.
So we basically manage that in production on a simple GPU, on one GPU, to actually have a 0.2 response time. Which I think make it possible even that we go for some uncertainty prediction if we parallelize that, for example. So it's a small model, relatively. Yeah.
So then after that we show the architecture. So the class we implement can be either the same one, can be either multitask or multi-label just by putting the number of tasks to 1. So here is our model. We use PyTorch, and for the here is the architecture. Sorry, and then for the model we use PyTorch Lightning, because for its clean implementation, we can use it to speed up the model training, for example, with the 16-bit precision. We also benefit from the distributed training around different workers. And here the implementation contains also the default PyTorch Lightning functions, as well as some other custom methods, which is the loss, which we're going to talk about, the custom prediction, and the threshold tuning. For the optimizer, we're using the Adam weight optimizer for its good generalizability, and we're going to also tune the weight decay of that function. For the scheduler, we tested 2 different schedulers. First one is the linear schedule with warm up, just so goes to just warm up from 0 to a number of warm up steps, then finishes to 0 linearly. And the second one, which we kept, is the reduced learning rate on plateau. So this just reduces the learning rate when the validation loss has stopped decreasing, and we apply the new learning rate, which we do the current learning rate and multiply it by 0.3. And this one yielded the best results, especially for the models training. For the models.
Selim, did you separate like the learning rate of these common layers from these class-specific layers, or does it make sense? Okay.
I just set up a generic learning rate. The learning rate was found by manual tuning. So just try different parameters and saw which ones optimize the results and training time at the same time, and especially for the number of epochs. And yeah, for the reduced learning rate on plateau, this is the one that did the best. There is we also do some early stopping, so just to be able not to lose time. Then for the loss function, we use the focal loss function, so because it helps us reduce the imbalancedness problem. It was originally made for computer vision tasks, and it's basically an adapted cross-entropy loss to imbalanced data tasks. Alpha and gamma here are some hyperparameters that change compared to the cross entropy, and basically what it does is get the curve make the loss more curved so it can fit better. We fine-tuned the alpha and gamma manually and found.
Sorry, it's funny that now it comes to questions for me also. So what is the PI here? I mean, what does it do? Is it different from each class? It does kind of weighting for different classes based on their imbalancedness?
The focal loss?
Yeah. What is that exactly?
The focal loss is just you have the cross entropy, which is just a more cross entropy adapted more to imbalancedness, so it helps adapt to the imbalancedness problem, because sometimes you don't have many samples to train on. So then being able to have a more curved when the loss is more curved, it helps fit better to the task.
Imbalanceness, you mean here imbalanceness between the classes, the number of training data that each class has. Okay.
We also
This PI, I think especially in the equation of focal loss. Yeah. I think this alpha and gamma is specified as parameters, but this PI or PT I cannot.
This PT is just the exponential of the minus cross entropy loss, and it's just used here.
There you see it. Yeah.
Okay.
So it's just the same equation.
Yes. Okay.
And then yes, we find gamma equals to 0.5 and alpha of 0.5, which do the best results. Does anyone have any questions about this?
How much is it important that you decide on that specific transformer model? I mean, like if we switch to another transformer model, how sensitive is the model to that?
I did not really go into that because I began by choosing the transformer model for the time and memory problem, and then tried to adapt all my work on it specifically. I did not try to compare transformers models across themselves. So here is then we just show the implementation of the class, basic PyTorch Lightning functions, and then we get the loss, then to just the custom predictions, the threshold tuning, etc. And after that we define another class which is used for training each different model. It contains one function, but it helps us get some modularity in case we want to make some additional changes after that to the models. Then one very important thing to talk about is how we train, how we monitor different models, etc. So first of all, we use we use AWS GPUs for training, and then we use MLflow for just monitoring. So here you can see an example of MLflow. Sometimes the training job works well, sometimes it doesn't work, and it also helps us deploy our models with the AWS endpoints. So here we can, for example, in MLflow, we can also monitor we can have somewhere to just find each model, the parameters it had, the results it had, so we can compare it later because across the team and see which models yielded the best results. So for inference, we used the PyFunk flavor of MLflow. And there is one other thing very important we worked on, which is logging, because right now we have 3 models, and one very important thing is we log them into the same endpoint. So we have 3 models, and we train them sequentially, train the first one, then the second one, the third one, but then we log them all in one endpoint, and basically this helps us gain 3 times this helps us divide the costs by 3. So we work on the structure, and for future works you can also do more. We can divide by, if we have more models, we can also add them to the structure. It's possible. So this is we use we use AWS, and some of the challenges were to deal with in the beginning we used JSON, for example. Then we switched to deal for all the logging, etc. Because of the robustness. There was also the problem of the multi-processing, because the models are distributed across different nodes. So we need to be able to retrieve them all so that it gets logged and we don't have an error. Yeah, these were some challenges we had for the deployment. Does anyone have any questions about them?
What do you mean from logging?
Sorry?
You said logging, right?
Yeah, we train the 3 models sequentially. We put them in our custom data structure, and we log that data structure into MLflow to have this kind of log. And then the good thing, this is what we do. And MLflow also helps us here monitor the models deployment, and when we put them into production.
Got it, thanks. So when you get a request, then you actually run all the 3 models
Exactly.
at the same
Then
time,
when
right?
we have the request, the model is logged into the endpoint in AWS. We get the request, and the models are run sequentially. Actually, first one, then second one, then third one, and then we have the output, and we will just show after a bit the output structure, how the structures are done, and how we post-process everything to have the clean results. So here we're just showing the columns we're training, no secondary tags, then some of the things we want to log. Then we also manually fine-tune the dropout rate, the weight decay, the max epochs, and the learning rate, depending on the dataset size. We also have something we do is the maximum number of repetitions, because basically we're training sequentially 3 models, and we want, if one model is performing badly because of some randomness, we don't want to lose everything. So if after training the model and doing the validation on the validation set, if the validation score is too low, we allow retraining using a lower learning rate and a higher weight decay to avoid overfitting and to allow the models to train better. So here we show our training, and after that here is just one run with just one epoch on the Google Colab GPU. But for our case, for example, we run with five epochs. Here we just run with one epoch, but we just run with 5 epochs in our main run. We also put a lot of effort and to find this optimal learning rates, because we just needed to do many loops on the learning rate, trying them. Sometimes it overfits, sometimes it doesn't work that well. So yeah, this is something important.
How long does it take for one configuration run
to run one model for all? Depends on the depends on the GPU, but with the one we're using, it's already 8 hours.
8 hours. But is it like a with GPU like this 12 gigabytes? Not so big, right? So just very simple.
It's
GPUs.
I forgot the exact name of the GPU, but it's not the basic one. It's the one upper level. I think it's the G3 to X large, something like that.
Okay.
Sorry, going back to the deployment from before. You said the 3 separate models. Are these not completely separate, or is the backbone still shared between them?
No, the backbones are shared across different layers of one model, but for the 3 separate models, it's the 3 separate backbones. So if the running is independent from a model to another. We also try to make the models together. So we try, for example, to merge secondary tags and primary and subpillars, because they have maybe not far architecture and didn't give that good result. So yeah.
Okay, thanks.
Thanks, Ivan. Then we just get the prediction, and here is the output structure. So we just try to combine all these structures together. So it's a dictionary. So it's a dictionary in a list of dictionaries. So it's a bit. We just want to have all the predictions for all the models together. For example, for this one, we have the probability of the agriculture. We want to output ratios, which is the ratio of the probability of agriculture divided by the threshold, because then we can just play basically with the ratio. If we want to over predict, we choose a minimum, we choose a ratio inferior to 1, and if we want to under predict, we choose it superior to 1. This also helps us in deployment, having the feedback of analysts saying, okay, this tag is not performing really well, it's never outputting anything, then we can just lower the threshold. And if it's saying, okay, this is over predicting, then okay, we just lower the threshold, and it just helps us after training with the fixed models to have some adaptability across different tags with low effort. So here we can see an example of the outputs of the ratio. Sometimes it's superior to 1. For example, in this case, only the cross tag would be output, and this one is really not far. And finally, for the subpillars, we just see all the structure. And then we just do a post-processing to separate the subpillars 1D from the subpillars 2D, and link the predictions of sectors and subpillars 2D, because, as we said, they are linked together. And so here we just, before having the results, does anyone have any questions about anything?
Selim, do you have also here the thresholds, the value, the optimal threshold that you found? Do you have it somewhere? I'm just wondering if there is any correlation between the amount of training data that we have.
Yes, I did not really do that, but there is a correlation. The more training data we have, the bigger the threshold. It can go up to 0.7 for the sectors, but then for the really underrepresented tags, it goes down to 0.01. So there is a really big difference, and tuning that threshold really could help us improve our results.
Yeah, there's definitely a calibration problem here to be solved. Yeah.
So here, for example, we can have an insight on the clean predictions. Here is the excerpt which we get by the user, the ground truth and the predictions. Right now, the predictions with just a low sample of data and just one epoch don't give good results. So they tend to over predict and give generally wrong results. We can also see some of the raw tags. So here for example, for sectors we have the perfect matches, meaning okay, the user selects an entry and how many times does the model give perfect results. Then there is when does it give at least one false, and when does it give at least one missing. You can also see here that they can be superior to 1, because we can have one false and one missing. So everything doesn't need to sum to 1. Here the results are not really good. We can show also the specific ones for sectors, for subpillars 2D and subpillars 1D. Now we show just our results we got with our training the whole models with all epochs, etc. So
just a comment. This is our very specific sort of evaluation metrics, because our problem is very specific. So it cannot be only precision recall or accuracy. So that's why we have these 3 specific evaluation metrics.
Yes, and because we also want to have the general insight of how the model is doing, but we also need to have more specific insight on each different tag alone, on its precision, its recall, and its F1 score. So this is something very important. Then we just show something similar, but with our data. Already there is some improvement. 69% of perfect matches for sectors as well as subpillars 2D, a little bit less for the subpillars 2D. Sorry, 69 for 1D. Then the proportion of at least one false is always so. Here, what we can see also is, for example, if we don't have a perfect match for anyone, it means there is at least one false, and this is something important to notice. But there are not many missing tags compared to the false ones. This comes from the fact that each tag is trained alone, and then each tag has its own recall and precision. So then, on the overall, models tend to over tag than under tag when you get the whole picture. Then we have the specific results. we draw the results using the F1 score and we have 3 different metrics. We have our strong results, where the F1 score is superior to 0.6, challenging results, F1 score between 0.3 and 0.6, and room for improvement results, where it's inferior to 0.3. So here we see for sectors, for example, they're performing really well, all strong results. And just talking about this, we had this metric of the raw metrics, but we also had some taggers feedback. So we just work with numbers, but we also work with analysts who get our raw predictions on some new data and tell us, okay, sectors are working well, this is not working well, and we already use that loop to begin working on our data, etc. So yeah, the sectors tag are performing well, but then for the sub-pillars, they're performing heterogeneously. We see, for example, that international response in capacities and response is performing well. However, some other tags are performing really badly. For example, local response and number of people at risk. Others are performing mediumly, let's say, with some challenging, almost only challenging results. Finally, for the sub-pillars 1D, we have even more tags. We have 33 tags in 6 different pillars. COVID-19 are performing well, but there are some other pillars which are really performing badly. For example, information and communication, where we already need to work on. Then we'll have other feedback, and then we'll have more feedback when we deploy our model to know what still needs to be worked on. Overall,
just a comment here also about the performance. I mean, the system is still has been shown to be very helpful for the annotators, for the users. What we are showing here is that we try to be also transparent, show also the parts that the model cannot be very well. But in general, the system has been very, very good, especially because the parts that you see that has the better performance are the majority of the classes. These are things that happen more often, and the parts that are less data that we have and the performance is also lower. But generally, the system has been very helpful for humanitarian sector. I should also add this point. But we can also show you that these are the challenges. We will love if you want to take this challenge and help us also for solving them and making them better.
Then finally, something interestingly enough is the tag's performance as a function of the probability of occurrence. So we see that the more data we have, the better the score is. Basically, interestingly enough, it's a log curve. So, for example, we don't need to have 20 or 10% of data to have a good performance. If we can generate new data points and just have a little bit more probability, it just augments the performance, augments really fast. I think this is also linked to the backbone itself. So the fact that it doesn't have many parameters, so maybe having more data can help it. After that, we're just comparing our model to the baseline. So, for example, in the baseline, we had 34% of tags which were performing badly, but in our model, it's only 21, and we see that we did some improvement compared to the fast-text baseline. The arithmetic mean of the F1 scores is also higher by point. We went from 0.39 to 0.49, and this is already a big improvement because we're just like I said, we're taking an arithmetic mean of all. So for the tags that are overrepresented are performing really better, but the ones that are not are really performing the same because they're underrepresented. So we should always remember that it's just like Navid said, it's an arithmetic mean. So having a 0.4 F1 score doesn't mean all the tags are performing badly. It means that some are performing well and others we still need to work on. Do you have any questions? Yeah. I think that it can be done, but the problem would be that the models because we also tried some different, in our experiments, we also tried different configurations. We tried to have, for example, different models for different pillars, not only one model for the whole. We tried some hierarchical architecture where we find first the pillar, then the sub-pillars. We tried different settings, and one of the settings we tried is to try to balance more the data by dividing the data into the ones that are performing well from the ones that are not, and it did not change much into the results. What do you mean, an explanation for why it did not improve? Intuitive idea, I would say that it's. I think that with what we're doing right now, with the threshold tuning especially. So even if the models don't really have many data, they just won't be confident because they just don't have enough information to work on and to fine tune the models. So I think that. If we try, we also thought about not giving the models all the data wouldn't always benefit them, because models learn from negative examples to negative examples. Just for everyone are the tags where there are not any sentences that are not tagged at all. So we also want the models to benefit from the negative entries. So I think that this is my explanation.
Yeah, then I add a little thing. Then another thing is that maybe we have to remember also that these are multi-labels scenario. Okay, so maybe there are some tags, some labels that are in some way correlated, and maybe there is some cases where you have 2 tags, or maybe also 3, 4, and maybe some one of them works well because are well represented, but maybe the other, referring to the same sentence, no, it's from maybe a set of labels that are underrepresented, and if you separate the data from more represented and underrepresented, then you lose also this kind of correlation in some way, and so you lose that one of the underrepresented. It's lost, and if you merge together, maybe there is some chance to have it.
If I may also add one thing, I mean, I believe what we learned after all of these experiments is that this standard regularization methods would not really bring anything special for our scenario. Like, let's say data augmentation, I don't know, adding some regularization loss, etc., because apparently this transformer BERT model is so well regularized that adding something more to that does not really help it much. It's already on the apex. It's already good enough by itself. Yeah. So, but what we probably need is more information, better data that we push it in. Great, so I guess that was all we have done good, and now the places that we failed.
So now we can move to the current challenges in our classification.
So fail you call the challenge, okay, no, that's good.
The data, especially, we just been talking about the importance of data. Then for the models, as we just talked about, there are some specific tags, for example, the number-related tags, which are not qualitative but quantitative tags, and being able to find, we have maybe 7 or 8 of them in all our models. Maybe it's important to find, the models don't always perform well on these number-related tags. So we're working on, and the presentation of of Ted from MIT of this morning was very interesting. Maybe we can merge our works together to try to have better results. Then there is another problem which we've been having is the organization-related problem. Basically, it's the national vs international vs local response. And even already for taggers, it's not always possible to see the difference. But our models are not working well, especially for the local response where we don't have many data. Finally, for deployment, we want to reduce the costs of deployment, work on deploying the models on CPU instances, or even better on Lambdas on AWS. That would reduce the cost significantly. And then I would like to introduce some other tasks.
Yeah, maybe to just wrap up in the, if you would be interested, just in case I'm, so far we just talked about one specific task, classification, and whole of our system has a lot of other challenges and other tasks that we also briefly will discuss about that, but we now go completely into this classification task. I can also just rephrase what's happening here. So one thing that we can really enjoy from that, and the system can be better, is a better way of generating data, let's say through active learning, for example, a more clever way that we can annotate the data, because we have the people who annotate that, but if we leave them as they are doing, we might reach to the same distribution of data as we have right now, and we might not have a necessarily better system in future. And then what would be the correct strategy to let them train the data or produce the data points that our system doesn't have any knowledge about, right? So how we can fill the gaps of knowledge in the system. That would be one very interesting question, and I think we are very interested into that also. Supported, that could be in any framework that you may imagine. And the other part that you see in that the specific modeling system, something probably like uncertainty, like calibration, can also help the system. So that could be also even like a research question in this specific context.
So we introduce the other talks, the other tasks we do with the NLP, in the deep. First one is the geolocation. So right now we're just classifying, but we also want to find geolocation depending on the entry. So what we're doing is we're using a spacey pre-trained named entity recognition multilingual model, which gives many false positives. So we do some cleaning and post-processing and keep only locations which are verified to be in the deep database, so that we're sure we don't give as many false positives. And the last thing we do also, which doesn't rely on machine learning, is the source reliability. So what happens right now is when a user, so before the user tag the source reliability, depending on the source, we have two different sources: the authoring source and the publishing source. So there are two different organizations and the users upload them in the beginning the project in the deep. So what we do is we compute the reliabilities of organizations, and then when a user uploads a document, we compute the reliability score. So for example here, if we have the authoring organization in the database, we just return it. Then if we don't have it, or if the user doesn't upload it, we just return the publishing organization score. And finally, like Nicolò talked about this morning, the next steps we want in the NLP, what we're working on, the humanitarian backbone. We're also working on automating everything for the text extraction. We want to do the natural language generation and the question answering using the data. Thank you for listening, and if you want any further information, feel free to reach to us.